Right now, you are sitting on something, and you are not falling through it. You probably think that's because the chair is solid. It isn't. The atoms in that chair are almost entirely empty space. So what, exactly, is holding you up? The answer is a quantum property so strange that the two men who discovered it panicked and tried to withdraw their own paper. February 1922. Otto Stern and Walther Gerlach boil silver in a furnace and fire a thin beam of atoms through a lopsided magnet. Classically, the atoms should smear out into one continuous band. Instead, the beam splits, cleanly, into exactly two spots. Here's the part nobody tells you. They weren't testing spin. Spin didn't exist yet. They were testing an older idea about orbits. Right experiment, wrong theory. It took 3 more years and 2 graduate students to learn what those 2 spots meant. 1925, Leiden. George Uhlenbeck and Samuel Goudsmit proposed something reckless. The electron carries its own angular momentum. It spins. Then Hendrik Lorentz, the most respected physicist alive, did the arithmetic. If the electron were a ball spinning fast enough to carry that angular momentum, its surface would be moving about 10 times the speed of light. Impossible. Uhlenbeck and Goudsmit ran to their advisor to pull the paper. He had already mailed it. As Goudsmit told the story, Ehrenfest just shrugged and said, "You are both young enough to be able to afford a stupidity." And here's the thing. Lorentz was right, and the paper was right because the electron isn't spinning. Nothing is going around. The electron has no measured size at all. There is no surface to rotate. Spin isn't a motion the electron performs. It's something the electron simply has. Like its charge. Like its mass. A fixed amount of angular momentum, built in, that it can never speed up or stop. In 1928, Paul Dirac showed why. Write quantum mechanics so it obeys relativity, and spin isn't something you add. It falls out of the equations, uninvited. His equation predicted the electron's magnetic strength, a number called G equal to exactly 2. Today we have measured it 2.0023193, correct to 1 part in 10 trillion. But spin does something far bigger than predict a number. It sorts every particle in the universe into 2 tribes. Whole numbers spin, like photons of light, are sociable. Pile as many as you like into the same state. That is what a laser is. Half number spin, electrons, protons, neutrons, everything you are made of, are the opposite. Wolfgang Pauli's rule, no two may ever occupy the same quantum state. Not, shouldn't, cannot. Electrons stack into shells because the lower ones are full. That stacking is the periodic table. That is every chemical reaction in your body. In 1967, Freeman Dyson and Andrew Lenard asked the obvious question, what happens if you switch Pauli's rule off? They proved the answer. Matter collapses. Every atom crushes down into a fraction of its volume, and pressing 2 ordinary objects together would release energy like an atomic bomb. So, it was never the chair being solid. Your electrons and the chair's electrons do push apart electrically. But the reason atoms have any size at all, the reason you take up room in the world, is that no 2 of your electrons will ever share a state. You have volume because of spin. It's in your doctor's office too. An MRI doesn't photograph your body. It flips the spin of the hydrogen protons inside you and listens as they tip back, which leaves one strange thought. Everything you have ever touched, you never quite touched. Does that make the world feel further away? Or does it make you feel like part of the same rulebook as everything else? If you want more of these, subscribe.